Hi, everyone. Thanks for joining today's webinar, Interpretable Machine Learning for Enterprise Applications. We have two speakers today from Grid Dynamics and Stanley Black & Decker. And before we get started, I just wanted to cover a few housekeeping items. So please note that your console is fully customizable and you can expand or collapse any screens. And also note that there's going to be two sessions today. So at the end of the first session, right at 2:30 in Eastern time, you'll see a button pop up, and it's going to take you over to the second portion of today's webinar. And we will answer all questions at the end of the presentation. So be sure to submit them in the Q&A panel on your screen. And we'll also be sending out the recording for today's presentation. So you should receive that in the next couple of days. And at this time, I'll turn it over to our first speaker.
Hey, everyone. This is Prabhakar. I'm the Director of Data Science at Stanley Black & Decker. And here's a quick preview of my experience. I have a bunch of experience in healthcare. I've been in automotive industry, remarketing, and industrial distribution and manufacturing. Today, I'll be primarily talking about how we implemented demand forecasting, and specifically for demand forecasting, how we implemented an AI/ML framework, and what type of problem is it solving, how big is it, and when push comes to shove, we go into production, what are the issues that we have to deal with, some of the interpretability elements. So as we talk about this, I'll talk about all the challenges of doing this at scale and doing this for a very, very large portfolio. Stanley Black & Decker, as you can see, a lot of these brands you will recognize, but one thing that's common between all of them is they belong to Stanley Black & Decker. And this is a huge portfolio of products. And not just these brands, you also start to see where we have security solutions, hospitality, healthcare, and fastening solutions and infrastructure products. So at the end of the day, any demand forecasting work that we have to do has to go across all of these different elements of the business. And one of the core challenges that we have is, all the complexity of these brands included, we have about 100,000 products. And based on how we forecast them, we almost have like 2.1 million demand forecasting units that we have to forecast across the globe. So as we go through this particular large challenge, what we see is we are now looking at a extremely large system where we have to provide the visibility of all the demand forecasts that we're generating. And we have to, again, make it easy to consume all of that insight across all of these queues. And when we first do the transition, you have to make a case for transformation, not just for moving to an ML model, but we have to handle physical business transformation that spans across the globe. So let's start with a very basic notion of why we even need to do demand forecasting. So demand forecasting is all about predicting customer demand. And when we think about what we do with demand forecasting, in the grand scheme of things, demand forecasting is essentially our way of establishing the baseline off which you measure actual orders, and the company then puts cash into the business, and then they build inventory. And that inventory is built on the back of working with the suppliers and the whole ecosystem that's created, that exists to support the creation of the product, and the resources and capacity all come together, all to basically fulfill the demand. So it's, in the grand scheme of things, that's where demand forecasting lies. And as you think about it, right, one always has to ask, like, why do I need to do AI/ML? We've all done demand forecasting in the past. There's very advanced statistical algorithms. What's different? So one of the things that's really different about the AI/ML formulation of this problem is the fact that you now bring the formulation itself to a single structure. You take advantage of data structures where everything is considered as a time series signal, and you bring together a feature library that is used to augment your understanding of data science. From a data science perspective, what are the things that impact your forecast. And one thing that's really different is how the features are handled from an ML perspective. The statistical forecast, typically the older algorithms that when we think about them, you still have to apply them from an individual time series perspective. And sure, there are algorithms like Varimax or VAR algorithm where you can build a model across all the time series together, but they fundamentally don't handle all the problems that are core to solving a multi-time series problem. And the AI/ML formulation handles that really well. But consequently, some of the things like model optimization, data size, then some of the insight infrastructure, and potentially how the algorithms potentially fail, all of those become new challenges now that you have to deal with as you go through this exercise. So let's start with what makes the problem itself very challenging. Now, data availability and agility. Everybody wants to use every piece of data and the new buzzword of big data where you want to build this properly and you want to add all the features in the world and have this very seemingly non-connected phenomena drive your forecast, and suddenly you have like a crystal ball, right? In reality, it doesn't happen that way. In reality, you have to invest and improve the quality of every single one of your time series to bring it together. You have to have a time series transformation system that you have to build where you look at all of these signals and you're trying to bring them together into a single feature library. And how you do that, what's the timing, what's the quality of the data, all of those pieces matter. And the other part that's really important is, from a formulation perspective, if you just purely look at time series, you kind of miss the larger impact of a product's life cycle itself on the forecast. So if you just think of a time series model and build a time series model, there are larger implications that can be learned from across products to understand where a particular product is in its life cycle, or what is the associated adoption with a particular product. All of those elements of a product's life cycle also need to be included when you're doing demand forecasting specifically. The other thing is, of course, the basic stuff, like you have to account for all the issues with the time series patterns, whether they're stationary, whether it's seasonal, trended, whether when it's irregular, it's fluctuating, or whether it's intermittent. There are times when you think of over time that even the distribution is not constant, and that's what stationary is. Intermittency basically means there's zero demand events, and seasonality is a repetition of patterns, and fluctuating is basically a full change in direction or a change in trending that happens over a inconsistent period of time. So all of these little elements now have to be accounted for in the model. And as you build, now since you're building an ML formulation and you want to do cross-validation across time, you now have to build a separate design of how cross-validation happens. Notice these are all design elements that happen while you are making the transition to AI/ML. And then you start to talk about the accuracy metrics and how you have to now start using non-scale dependent metrics to go across multi-time series, because magnitudes of the different time series themselves have an impact on how the accuracy is calculated. And when you try to build an accuracy metric that goes across, say, 1,000, 10,000, 1,000,000 different time series, the way you weigh the way you handle the error term, and when you run the optimization algorithm on top of the error term so that you find the best model parameters, it changes how the results happen, and you could penalize smaller magnitude terms versus larger magnitude terms, and you have to start to then think about an accuracy metric that balances out. Now, then comes AutoML. There's a lot of opportunity now to, once you've scaled the approach on the data side, made the created this set of features that can handle and record certain elements of the data, like seasonality, potentially a derivation window of features that represents how you can think about autocorrelation. All of those elements, once you think through on the data side, then it comes to AutoML engines. Now, we use DataRobot on our side as the AutoML engine, apart from our own custom algorithms that we run along with it. But what happens is AutoML, one of the key challenges while using AutoML is when you bring it in, you almost have to understand, people who build the AutoML have their habits incorporated into AutoML. So you have to always take a very deep look at the AutoML engine you're using, and there are ways to take advantage of all the automation advantage it brings and all of the best practices it brings, but also be very, very understanding of the limitations of said approach, and ensure that you are not fixing a hyperparameter that is now a hyperparameter because of how the engine works. So you have to be very careful. The other thing is AutoML engines, as they start evaluating a lot of models, the size of the data set that's the input to this exercise also matters, and how you manage it, and so that you don't end up biasing the AutoML approach. Or you put things like shorter history time series with long history time series together in the same project, and then you end up with a mix of skews where the error term you select might penalize one type of skew versus the other. And the choice of models, everything that you derive might be for a subset of models, it might be underperforming on a subset of models. That's where you might have to think about creative ways of grouping the time series before they go into AutoML engines and things like that. So that's one of the key design elements as you think about it. So when somebody now builds a crystal ball, now the question is, what goes into the crystal ball, right? And I won't go into all the technical details, but I'll talk about how these are designed for downstream interpretability and integration with our business teams. So a lot of what we do, the feature expansion engine, is a lot about how do we create features to address all the data-related issues, like the lifecycle issues, the different features associated with different things that impact the prediction itself, which is the feature engine that you see here on the left. And what are the different scaling and those issues, how are they going to get handled in the sampling? All of those things get tagged upfront in the feature expansion engine. The correlation causality engine is our way of taking that feature set and creating a connection between all of our features and the connection at various lags, so that beforehand we do an analysis of what features we could reduce way before going into the analysis itself. And we have a halo cannibalization engine, which basically takes the correlation and causality connection and identifies the subset of time series that basically they have a halo impact. A halo impact is defined basically as you have correlation at a particular lag, and that correlation is Granger causality tested, and if we find causality, then the direction of correlation, if one grows and the other decreases, there's a negative correlation, then it's a cannibalization impact, but it's a halo impact if it's positively correlated. So we have those types of engines that do more with the time series and tag them beforehand and become the source of explanation. So when we get this result out, what we are doing is, as we find shorter history time series, we do imputation to basically fill up the history for those skews where there's not enough history. So we artificially create synthetic history so that we take into account things like the life cycle of a particular skew. We take that history from those skews that have had a longer history, and we find shorter history skews that form similar patterns. So using the clustering engine, we also have a generalized low rank based imputation engine. These two together create imputed time series for us, where we have to deal with really short history time series. So all of these together then go through the custom modeling engine, and they go through the AutoML modeling engine simultaneously, and then we pick the best model out of both exercises through an external engine. And sometimes we even look at the possibility of creating an ensemble across both engines. And after all of that, we produce the best batch of forecasts for the best model through best model selection across all of this. Now, for about 5,000 plus time series, we run close to like 800,000 models, and we've pushed the envelope on how we code this in Spark to do this, in like 7 or 8 hours versus taking several days to do more. And we are making further investments to increase the scaling of the algorithm so that we could handle 2.5 million time series in a few hours. As we go through this exercise, one of the things that is really key to this exercise is the meta-analysis engine. And it's basically the idea that you built a model. Now you take all of the tags you generated through the first 3 exercises and use that as a way to explain how the overall modeling strategy is picking the winner and what are the driving forces. So when we do a one variable to single variable and bivariable partial dependency plots, we are now able to show the sweet spots for the models to get implemented, and that's a very good way to communicate with the business to share that. Now, one thing is, as you go through this, we have a lot of code as we build through this, and all of it is about, the backfilling of the history and how we bring skews together. And all of it takes into account the key things we talked about in the first half. What are the things with demand forecasting? And as we go through this, our roadmap is all about how do you take the business from a thoughtful action that's now a basic insight-driven process, and you take it into the future. We start to do basically automated integrations, and we do a forecast value-added analysis that's downstream that actually takes an existing statistical system, applies our recommendation as an adjustment so that it gets adjusted to our forecast number. But we take every element of the demand planning process and incrementally calculate the value add. So that gives us a clean framework to identify the amount of value we've added through this exercise. So now, what does the mutual operating model look like? We have a very focused operating model where we engage the business and then do the ideation. So as we build through this process, all the hypotheses that were generated that led to the analysis of the features and the different demand patterns and the picking of picking of the right accuracy metrics. We did in the first 3 phases in the development, we really scaled out all the elements of design that led to us building a full end-to-end pipeline in a CI/CD framework on AWS. And that's also partly one of the reasons we chose it was for future scalability as we scale to more and more time series. Now, from a big picture perspective, I think I always hear of people using forecasts as a way to say, hey, how is the future going to give me a precise answer? But the goal of forecasting is not really to predict the future. It's basically to understand that baseline that lets you take a meaningful action. And understanding this piece is really important because as you come together and you look at the overall picture in which demand planning and forecasting fit together, it's a very small part of it. What the real activity is, strategy basically uses forecasting as a baseline to understand, given current course and trajectory, where we will end up. The goal for a company is what is the goal for a company is the goal for the company. And then the delta between the strategy and the baseline, strategy outcome expected and the baseline is what you need to do more planning for. And you basically fulfill the delta through more strategy and planning, and you go back to the analysis on your results, if it worked, if it didn't work, and then you wash and repeat. So in that sense, forecasting is not the end in itself, it's the means to do better organizational planning. Now, the new trillion-dollar question seems to be COVID-19. And some of the key things to take care of during this particular situation is all models are likely to be wrong, especially if they come from a place where you're a data scientist and you go, I didn't do any previous training in epidemiology, but I'm still going to go build a forecast. It doesn't work that way. A lot of research needs to be done, and you need to kind of engage experts as you build these. And then every time you want to establish a forecast number, should express the level of uncertainty that you have with this, and also communicate, what is your expertise on the matter itself, so that people understand what is your background and how much work have you done to understand the model and before you can add to it. And also be as transparent as possible. If you are just making a time series prediction, then that's also something that you need to be very transparent about these things. Now, for models that are already deployed, I think the key thing is always, first keep your data scientists healthy, because they need to be there to ensure that the models don't break. Then the right thing to do is to prioritize the models and monitor based on the amount of business impact. If there's one of the other things is that always check if the main hypotheses of the model implementation has changed altogether. For example, if you are building the model from the perspective that there is a main customer in, for example, the industrial sector, and that was the main roster of customers. Now, knowing how the industrial sector has really, really been impacted in the last 3 months, to continue to use the model would be folly if that's the data and that's what it's based on, because the whole industry is not the same. That sector is not the same. Then also check for anomalies, because one of the things that is going to happen is you can make a prediction, but one of the biggest things that's going to change is you have to train often. And you have to ensure that that the anomalies are all addressed, and also that the original hypothesis hasn't changed. And as you set up the problem going forward, you have to ensure you have to prioritize visibility and the accuracy of the data itself.
Hello, everyone. Thank you for joining this Data Points webinar presented by Grid Dynamics. And the topic of our talk today will be interpretable forecasting models. First of all, let me introduce Grid Dynamics. Grid Dynamics is a data science and engineering services company headquartered in Silicon Valley, and we're in business since 2006. And over that time, we used to work with many retail, manufacturing, technology, and media companies on different innovative programs related to customer intelligence, revenue management, supply chain optimization, and other areas. And in this talk, I'm going to describe some of the techniques and some of the challenges that we were facing in different projects related to revenue management and inventory optimization and other applications of time series forecasting, as well as how we used to solve these problems on real projects. So I'm going to start with a description of several use cases for interpretable forecasting and signal decomposition. I will be using demand forecasting as a running example, and will be focusing predominantly on this use case and this domain, demand forecasting in retail and manufacturing. But also I will touch briefly some other applications that can use similar techniques like causal impact analysis in marketing applications and anomaly detection in IT operations. And after that, we will talk about what interpretability actually means for different users, in the enterprise. And finally, the main part of this presentation will be a hands-on tutorial, hands-on example that shows how different specific techniques can be used to decompose time series and how these techniques can be applied in practice to our example with demand forecasting problem. So let us start with the problem of demand decomposition and demand for revenue forecasting. So typically, when we are talking about revenue optimization or price optimization, the solution for these problems is based on the ability to forecast the demand based on the function of different variables like prices or promotions or competitor prices. And this problem is quite challenging because the number of different effects that influence demand on a certain product is relatively high, and all these effects need to be modeled correctly, and ideally we need to understand the impact of each of these effects. For example, if we are talking about some specific item like a coffee machine that we are selling, obviously the demand on this item will depend on its price, and can be different components of this price. It can be base price, it can be promoted price or discount. So we need to measure all these effects. But in addition to that, the demand on this item can be influenced by some other similar products. So consumers can switch from different brands or for alternative products back and forth, and we also need to measure cross elasticity of our demand on a certain item, comparing to based on the prices for similar or substitutable items, and it can be done within category or cross categories. It also can be dependencies between related products. For example, if we are selling coffee machines, that the price on coffee machine can influence demand on coffee filters because these are related products, and the more people use coffee machines, the more they use coffee filters and so on. So we need to measure this as well. We need to measure cross elasticity for competitor pricing because customer can switch from our brand to competitor brand and so on. We also need to track different temporal dependencies even within a single time series. For example, if we put some product on a discount during holiday season, then people can buy more units or more quantity of this product, and it will negatively impact the demand in the future because customer can stockpile certain units, especially for consumable products, and the future demand will be negatively impacted by that. And of course, there are some other external factors, external covariates like intensity of marketing campaigns, intensity of advertising that can also influence the demand and so on. But unfortunately, we are not able to observe all these factors directly. What we typically able to observe, of course, sales data, and it can be somewhat limited as well. And we also can observe some pricing information. We can observe, we can get some marketing data. But what we ideally would like to do, we would like to take our sales data and decompose it into these different effects that can include seasonality, that can include one item price elasticity and price response on our own product price or response on discount values, and also can include cross effects with related products or competitors. And this information needs to be derived from the sales data and ideally needs to be presented to business users, to price managers, so they can make decisions with regard to price optimization more efficiently, and also measure the response, the outcome of their pricing decisions more accurately, because it's generally not a good idea just to ignore cannibalization effects. You can run some discount that can change your sales volume for a given product, but it can cannibalize demand on other products, and the total ROI of this action can be zero negative. And this is something that we ideally trying to avoid when we build these solutions. So this is one of the use cases, and we will use it as a running example during this presentation, but this is not the only use case. Of course, there we need signal decomposition and interpretability of forecasting models in enterprise applications. Another good example is causal impact analysis for marketing actions or for introduction of new products, as it's schematically shown here. So basically, let's say that we have some history of our KPIs, for example, sales data within certain category, or number of conversions on our website, and then we do some marketing action, some intervention, for example, introduce new product or launch a new campaign. And we're generally interested in measuring the difference, the uplift between no action baseline, which we will not observe, and we can either somehow measure it using A/B testing, or we can use forecasting to estimate how this baseline will look like. And then we will observe our actual numbers, and then we will analyze this difference. But to do so, it's not always possible to do A/B testing properly in some applications like new product launch, for example. And it can be more preferable to do this forecasting and measure the uplift based on this forecasting. And it generally requires to separate normal effects like seasonality and other things from effects induced by, for example, our marketing campaign. And in that case, this essentially boils down to the problem of signal decomposition, or to some extent, interpretability of our forecasting ability to decompose it into different factors, different components and effects. Another example is anomaly detection. Imagine that you collect multiple metrics from your application or from your infrastructure, and you would like to send alerts to the operations team in case you detect some abnormal behavior. And this problem generally is very often solved again through special types of forecasting models. There we try to forecast how this metric should normally evolve, and then if we have significant difference between this normal behavior, this expected behavior, and what we actually see, then we raise an alert. And that all, again, it requires to understand what is normal behavior and what are the regular patterns in the observed metrics, and separate them from anomalies. So again, the problem can be framed as a problem of decomposition or problem of forecast interpretation and ability to properly interpret different components in the forecast and separate them in different ways, slice and dice them in a certain way. Okay. So these are use cases that we will be using during this presentation. And now let's talk about what interpretability actually means for different business users. And again, let's use this demand decomposition and price optimization use case as an example. From the data scientist perspective, when we are talking about interpretability, typically it means that we have some model, and this model either allows us to directly trace the dependency between changes of certain individual features or group of features and its outputs, or we can use some techniques like Shapley values to essentially estimate the same dependency, but for black box models. And using this analysis, we essentially, for most of the models, we can, for example, analyze if we change one of the features, it can be price or can be discount, how it influence our output forecast, for example, our sales forecast. But this is only part of the story, and this interpretation, it can be appealing for data scientists, but actually, in our experience, it's not necessarily appealing for price managers or for other business users. And from the business user's perspective, the interpretation can be substantially different. For example, one typical way how price managers would look at the problem, it's a little bit more extended comparing to this basic definition of interpretability. Again, we can have some forecasting model as the core of our solution that allows to estimate the dependency between, let's say, price and sales data. But at the same time, price managers might be interested in analyzing impact on different business metrics like profit, like ROI, like uplift, and it can be quite many of them. It can be tens of different metrics that needs to be analyzed. And this generally requires to build this additional layer of econometric models on top of our core forecasting model to measure all these different effects and measure how our input feature or change in the input feature actually related to changes in this business KPIs. And in addition to that, we can actually we might need to build even more models on top of that. For example, it's also typical for price managers to compare not just to forecast the performance of a given promotion, but to compare performance of this promotion with last year data for a similar promotion or for exactly the same promotion that was executed exactly a year ago, and do some experiments, some what-if analysis to see how tweaks in time or tweaks in discount value actually change this difference comparing to the previous year. So do we increase promotion performance by tweaking this variable? So do we decrease it? So in general, it's quite common to build all this machinery, all this econometrics on top of forecasted models to make our interpretations in terms of these differences more consumable by business users. And in many cases, one needs to go even beyond that and estimate not just these average numbers, expected numbers, forecasted numbers, but also estimate different statistical properties like confidence intervals or even distributions of these different metrics like profits or ROIs, so that marketing managers or price managers can make more intelligent and more safe decisions taking into account this uncertainty in the model. And this is another way of another perspective on interpretability is that they need not only to understand the dependency between the features and outputs, but also understand these uncertainties associated with the forecast. And in many cases, it can be done by building this pipeline with these forecasting models attached to econometric models and running some historical data, for example, previous year data through this pipeline to essentially generate this empirical distribution of our business KPIs, and it typically works pretty well and provides good insight into what this uncertainty ranges, and it's very well explainable to the business users in most cases. And actually, in reality, if we go even beyond that, and we are trying to present the results of our analysis or forecasting to the business users in a way that they can quickly do and efficiently do adjustment of their promotion parameters or pricing parameters, then typically it is done in the form of some interactive tool that they can change some parameters. For example, as you can see here, like promotion depth and promotion time frame, and if they change it, they can see how it is related to the price elasticity, and it can be derived, of course, from our forecasting model. We can forecast minimum possible demand and maximum possible demand based on minimum and maximum valid prices for a certain product, and provide some information. What are the elasticity ranges? For example, elasticity ranges are typically higher during the holiday season rather than other periods of time. So price managers can see this information. And it's also important to provide some insights into how individual actions like individual promotions affect long-term outputs, again, because of the effects that we just talked about, like cannibalization or pull forward effects. It can be the case that we can achieve good results for one product, consider it in isolation, but our long-term return for entire category can be actually negative because of cannibalization effects, or it can be negative even for this individual product because of pull forward effect. We can essentially pull more demand into this time frame, but in the long run, we will make less profits or less revenues based on that. And in practice, the design of these tools, it's significantly influenced by specific enterprise, by specific client. It's very, because business processes are very different, and questions that are asked by business users are also very different. They might be interested in finding top and top 10, for example, cannibalized SKUs for a certain product, or understanding the demand drivers, what are the positive and negative contributors into sales, like is it better to change baseline prices, list prices, or discounts, and so on. And typically it's quite challenging to, even if we have good forecasting models and we're able to estimate these basic dependencies between inputs and outputs in these models, and we're able even to estimate different components like cannibalization, pull forward, still it's often a challenge to present it to the business users in an efficient way and create tools that can be used efficiently and can be embedded into enterprise processes. So this was a kind of an overview of what I mean by interpretability in the context of price management, for example, and it's similar to other enterprise applications. And now let's go into hands-on, more technical session that we will talk about specific techniques that can be used to produce these different measurements, these different values that quantify all these different effects that can be used to build tools like we just discussed. And we will make this Jupyter notebook that implements this example available after this webinar. So I will just show essentially some screenshots, some plots out of this notebook for the sake of time, so we can go through it relatively quickly. So in this hands-on example, we will use generated or simulated data that reflect different econometric effects that we discussed. And the reason for that is that we would like to, in this example, we would like to understand how different interpretation techniques work for different cases. For example, how does it work for data with cannibalization versus data without cannibalization? And it's quite difficult to do it with real data and demonstrate it quite clearly. But in practice, these techniques can be very similar. And of course, they will not work so perfectly with real data as they will in this simulated example. But our main goal here is to understand these core concepts and see how it can be applied in principle to this type of problems. So our first step is to set up our environment, to set up the data, and the way we approach it, we first generate what we call here market envelope. So we essentially generate the total demand for some collection of categories for a long period of time, for 5 years. And the way we generate it, we have here some trend, and we also have some seasonality, and we have some correlated noise here added as well. And then we split this total envelope into demands for 2 categories, and there is some trend. So initially we have one category with larger demand and another category with smaller demand, and then the second category grows more rapidly comparing to the first category. So we generate the split with these trends and of course noise. And finally, we split each category into 2 products. So we have 4 products in total, and for all these products, we have seasonality effects at the scale of quarters, and we also have smaller scale seasonality at the level of weeks. So we have some weekly pattern which you can see here as well for all of these 4 products. Okay. So these are our envelopes, and on the second step for preparing this data, we develop some very simple econometric models that we will apply on top of these envelopes. So we will first, of course, generate some price series for each of the products. So we change our prices this way. Over 5 years, and we have some price response function defined here. It's very simple. It's a linear function, so you can see here that it is essentially a negative of the price. The higher the price, the lower the demand, and other way around. And then we also create series that simulate within category and cross-category cannibalization. So this series essentially proportional to the ratio between product own price and average price within the category and average price in the other category. And then we also simulate pull forward effect through generating this shaper that essentially tells us that we have negative impact on the demand after we raise the price. So we generally assume that once we raise the price, people start to use the units that they stockpiled in the past instead of buying this product in the store. And this effect has some prolonged effect, like 100 days, and over time, it of course decreases. So we have the series that models pull forward effect, and then we combine all these components into one shaper, price response, cannibalization, and pull forward. And then we apply this shaper to envelopes that we generated on the previous step. So this way we obtain sales series that have all these econometric effects as well as trends and seasonality effects that we generated in the previous step. And of course, we can turn on and off these different components. For example, we can turn on cannibalization and turn off pull forward, or turn on both cannibalization and pull forward, and then see how it changes our analysis. And we will do it in a moment. So and next, I'm going to talk about 3 different tools that we can use to analyze series like that. These tools are quite different, and they're not like perfectly substitutable. They actually complement each other, and in real analysis, it generally makes sense to use maybe 2 or these 3 tools together. And of course, this is not a full list of tools that we can use. There are some other techniques that can also be very helpful. So let's start with first tool, which probably is most common, and I'm sure that this technique is generally familiar to most of you. So we first use gradient boosted decision trees to develop the forecasting model. So we used LightGBM, or we can use XGBoost pretty much in the same way to forecast sales of products based on features like product ID, category ID, calendar features like day of the week, month, prices, of course, for this product and for other products, and different lags for sales and prices. And this way, you can see here that we fit this model reasonably well. This is a 7-day ahead forecast that we produced. We have this time frame for our training as our training data, and this time frame as our forecasting for test data. And once we fit this model, we can use SHEP library to estimate contribution of different features through computing SHEP values for all the features that are inputs to our model. And here you can see the result of this analysis for 4 different scenarios. So we have 4 different scenarios. In the first one, we have just the seasonal effects without cannibalization and pull forward. Then we turn cannibalization. In the third example, we have only pull forward. And in the fourth example, we have both cannibalization and pull forward turned on to generate our series. And the result is of course very expected, very predictable. So if we do not have, for example, cannibalization, then our price values for other products in the category or in other category, they score relatively low here, so we do not have much contribution. If we have cannibalization, then of course we are getting these values scored much higher, and we can see here if it produces some positive impact or negative impact depending on what we have. Do we have cannibalization or do we have halo effect? And this way we can at least quantify the impact of cannibalization to a certain extent here. But this is probably not, this is most common representation of Shapley value analysis, but this is not the only representation. What we can do alternatively to that, we can actually plot Shapley values for certain features for every time step, because in case of Shep library, it returns us these values for each time step and for each feature. So here we just squash all these values into this scatter plot. But alternative representation is to just take our time axis and visualize these contributions for every single time step. So here you can see again these 4 scenarios with different combinations of pull forward and cannibalization. And let's say if we have only seasonality without these economic effects, then we see that we can plot here these sharp values for sales forecast, and we can plot here this green line product price as well, and we see that product price actually is pretty much the only contributor to changes of our sales numbers, comparing to prices to other products. In case we have cannibalization, then we can see very clearly that actually prices for all 4 products, they have some contribution to sales data for one certain product. And this way we can see more clearly how exactly this dependency evolves over time and how it changes over time. Maybe it can be correlated with holidays or some other events, or some other pattern can be spotted if we do this analysis. So this generally a useful tool for cannibalization analysis, of course. So this is one of the techniques that we can use, and it's probably the most simple in application. But this is not the only technique that we can use, of course. The second tool, the second technique I want to talk about is vector autoregressive models. So this technique is actually I think it's not very commonly used nowadays in industrial applications, but it's very common, probably most common technique used in economic research. So these models were introduced in 1980s, and they were designed specifically to analyze multiple series of data, like in macroeconomics, it can be GDP and unemployment rates and some other series that jointly evolve over time. And this technique was designed to provide ability to estimate causal dependencies between multiple time series, and what we most interested in to estimate the dynamic response on one of the variables from some shock in other variables. So let's see how it works conceptually first. So the definition of VAR model is relatively straightforward. We generally assume that for each time step we have a vector of observed variables, and in our case it will be a vector of 4 values, like sales values for 4 products, and then we essentially model this value, this vector for a certain time step, as a combination of values for previous P timestamps, and P is a hyperparameter of the model. So we have these P matrices with coefficients, and these matrices, they are time invariant. And in addition to that, we have this error term, or this sometimes called innovation, something that we enter on top of it. that does not account, that does not fit these first terms. And one of the key advantages of our model is that we can actually estimate this dependency between these error terms and our observed variables and between different pairs of them. So we can see how one error from one of the series, one innovation in one of the series impacts development of another variable. And this way we are able to establish dependencies between different variables that we have in the model. And this dependency can be quantified, even more importantly, this dependency can be quantified in dynamics. So it's not just a single number, but what is called impulse response function. So basically what impulse response function is that if we have some change in one of the variables, for example, in price, just one single impulse, like a short-term unit change, then the VAR model can provide us insight into how it changes the dynamics of other variables, for example, of sales. So here in this example, this is just a sketch, but the idea here is that if we raise prices for just a short period of time, then people can start to switch to some other brands, or some other effects can take place, and the response actually can be somewhat prolonged, and it can change our demand for a relatively long period of time until things stabilize. And we are generally interested in quantifying these dynamics as well, because it obviously related to effects like pull forward, but it also can help to estimate other aspects of the data we are trying to analyze and consider behavior. So here we have an example that was generated of these impulse response functions that was generated from the same data we used in the previous example in the following way. So first of all, VAR model assumes that the data is it does make some assumptions regarding data stationarity and some other properties of the series that we are trying to analyze. So in order to make our time series compliant with this, what we do here, we actually feed some low capacity gradient boosted decision tree model first, and then subtract predictions of this model from our time series, and then apply VAR model to this residual data. And as you can see here, what we are getting out of this analysis, we can see that first of all, the response impulse response function between product own price and product sales values, it very clearly indicates the presence of pull forward effect. So we are not getting like this long exponential curve that you might remember we had in the original shaper, because we already applied our low capacity GBM model to subtract some seasonal patterns and other things that we do not need in the VAR model. But generally it's possible to quantify these time effects using this technique quite clearly, and it provides us with quite clear differentiation between series with and without pull forward effect. And actually for cannibalization, we can obtain the same insight through measuring impulse response function between price of one product and sales data for another product. And here you can see that if we do not have cannibalization factored into our data generator, then this dependency is essentially negligible. We do not have the magnitude of this dependency is very low. We have just noise. But if we really have cannibalization, then we have much higher magnitude, and we can see how price of one product influence sales on another product, and potentially we can do this analysis to see the actual dynamics, like how long lasting this effect is. So in general, this is a very useful tool, and not only for this impulse response analysis, but also for analysis of other causal dependencies between different time series, between product sales data in particular. And the third technique that I wanted to talk about is Bayesian structural time series, which is a kind of an emerging technique. It was introduced relatively recently, or at least it was introduced to industrial practitioners relatively recently. And I think the popularity of this technique generally grows. So let's talk about it. So this technique is based on traditional Bayesian hierarchical models that are used in many applications, in particular in economic research, in medical research for a very long time. And I just want to quickly summarize what Bayesian hierarchical models are about. So in general, this approach is about defining a certain model with a certain structure and inferring this model, parameters of this model based on observed data in Bayesian way. And for example, let's say that we observe some ROI numbers for different locations of our enterprise, for example, for different stores. And it's in this example, this is not time series. This is just, let's say, some monthly numbers or some annual numbers that we observe. And we make some assumptions about the process that generates this data. For example, for simplicity here, this is a very simplistic example. Of course, we can assume that this data is generated by some normal process. They have normal distribution. But in addition to that, we can make an assumption that actually these numbers, they can depend on location, for example, on state or on country this data comes from. And this will essentially some latent variable that we do not observe or might not observe explicitly. We might not have this country or state tag in our data. Let's assume that. And essentially, our observed numbers will be a mix of different normal processes with different means, and we can assume that these means are generated by some other random process. Let's again assume that this is a normal process defined on top of the first one, right? In that case, our data generation process is supposed to be as follows. We take our normal distribution, this one initially, generate some mean, then generate a number of samples here, then take another mean from this distribution, generate more samples in here. And our goal, once we are trying to fit this model, our goal is to estimate the distribution of our model parameters, these hidden variables that we do not actually observe. We just assume that they structurally should be present based on some common considerations, right? And we can estimate the distribution of these parameters based on data, and then we can, of course, estimate the distribution of the data that we observe and make some forecasts, generate more samples based on this distribution. And in case we apply the same approach for time series analysis, the concept will stay the same, but the model, of course, will be more sophisticated. Essentially, we can, what we normally would do, we will have some data, like let's say our sales data, and we will have some cover rates, like that we observe explicitly, for example, our price numbers, but we also can assume that there are some hidden latent processes that evolve according to their own trajectories, but we do not observe them directly. For example, it can be something related to seasonality, it can be some cycles in the data, it can be trends. We do not really know if these cycles or trends present in the data. We need to estimate these parameters that will tell us if they actually present, or these parameters are like zero and these effects are not present. And we define some laws according to which these hidden processes evolve over time. And then we fit this model using our data, and we estimate distributions of these different parameters, and it enables us to estimate the distribution of our output data, provided this model structure and these parameters. And it essentially enables us in turn to forecast future values and forecast the distribution of these future values. And also, if we estimate these parameters, we can decompose our observed time series into these different components that correspond to seasonality or trends or some other some other effects that we assume to be present in the data. And there are different ways how it can be implemented. There are a number of probabilistic programming libraries. Relatively recently, TensorFlow probability added their own implementation of structural time series, which probably one of the most convenient tools available now for these purposes. So here you can see an example of how we define our BSTS model for analysis of the data we used in the previous examples. So we essentially, this definition, in a nutshell, it's very straightforward. We can define some seasonal effects like day of the week effect, month of the year effect, trends, price effects as a essentially linear regression, and then model our output time series as a sum of these different effects. Of course, in reality, it's more, in real applications, it's more complicated than that, because we need to care about some other things. We need to care about hyperparameters, about priors to do that, but still, it's a very convenient way of defining our forecasting model. And then what we can generate out of that, we can take our sales series, and we can take our price data as well, because we observe them explicitly, and run it through this model and produce this decomposition of our sales data. And typically it works reasonably well, in the sense that it's able to forecast these daily patterns, monthly patterns. Here you can see that we also identified trend reasonably well. It's still, there is some leak of seasonal data into this trend, but it's relatively smooth. And also here we have estimation of how different prices on different products contribute into how observed sales data, and also how price sales lag contributes into observed data as well, so that we can use it to estimate our pull forward effect here. And we also get in, because this is a Bayesian technique, we also get in our posterior distribution for all these parameters. And here you can see these blue zones, they correspond to our uncertainty ranges for this data. And this is also, of course, very helpful, because we can see here not just our average forecast, but we also can get some idea of how accurate this forecast is, or how accurate our analysis of these different components is. And this is obviously a very interesting tool, relatively new, and in general we are trying to use it more extensively and more intensively going forward, instead of using more traditional techniques like Shapley value that they've shown in the first example. So now let me conclude this presentation with a brief summary on what are the main practical challenges in using all these techniques. The first major challenge is, of course, the problem of scalability, because in this example, we did analysis for a very toy example with just 4 products. But of course, forecasting, doing forecasts and doing interpretation of this forecast for 4 products is very different from doing it for 400 products, for example. And because if we have too many products, then we will have a lot of noise in this data, and contribution of each individual product, of course, will be like relatively low, and so on. So it's quite difficult to separate signal from noise in that case. And the way how we can work around it, there are different ways. Quite oftenly, people start with manually defined cannibalization groups, so just using domain knowledge and experience. Price managers and analysts, they can group products into some reasonable groups and make assumptions that there is no dependency between these groups, but there is dependency within each group. And then of course, the disadvantage of this approach is that it needs to be manually done, and we can do generally better than that through defining some automatic distance metrics between the products, or similarity measures between the products based on product descriptions, attributes, sales information, and this way we can generate these groups in automated way. But this is, I would say, this is a large problem in itself, and we can spend quite a lot of time talking about how exactly this part can be handled. The second large challenge is, of course, the lack of data and lack of variability in the data. For example, it's quite common in many applications that, in many enterprises, that only a relatively small subset of products is actively promoted or actively managed, and for remaining products there are no much promotion information. These products can be put on promotions very rarely or never at all, and it's quite difficult to, of course, in that situation, to estimate how promotions or some other changes in prices can influence revenues from these products. And this problem can be partly alleviated again through similarity analysis between the products, but in some cases one needs to do experimentation and collect more data for at least certain products selected in a certain way to make this analysis possible and accurate enough. The third challenge that we already talked about is how we can present the results of our analysis to business users in an efficient way. And it's of course very important, because we can develop a very good forecasting model. We can develop excellent interpretability tools using, for example, some of the methods that we talked about. But if we fail to communicate it to business users efficiently, they will just abandon the tool, and the business outcome, the final business outcome, will be zero for a project like that. And by this reason, it's very important to understand the business metrics, to understand how business processes work, and how these insights generated out of the models can actually be used in these business processes to efficiently adjust promotion parameters, to efficiently adjust prices, and what makes sense and what does not make sense for business users like price managers, and how this information can be summarized efficiently and presented to them, and essentially packaged as some interactive tool that they can do their analysis and observe some forecasts for business KPIs and so on. And finally, the fourth challenge, also very important, is validation of these different insights and forecasts. When we are doing this modeling, we, in most cases, we of course can do some basic validation using historical data, using cross-validation, test sets, and so on. But it's not always possible to validate all the things just based on historical data. Or it can be very challenging or unreliable to do so. And from that perspective, it's I would say it's always a good idea to incorporate some production testing or some trials, real-life trials, into the project roadmap, and start to do these first validations as early as possible, so that we can actually make some real business decisions, at least at a small scale, using initial outputs of our models, and execute these decisions and collect some feedback data and make adjustments to our solution as early as possible in solution development lifecycle. So all these aspects in practice are very important, and this is of course not the full list of challenges, but in general, these decomposition techniques, they play a very important and probably increasingly important role in enterprise applications, because black box models, of course, represent a lot of issues, a lot of challenges for business users, and at the same time, development of good interpretability tools, capabilities is also not straightforward, as we've seen through this presentation. So that's pretty much it. Thank you for your participation.